All right, so a little bit about me. My name is Sarah Marquise. I am the Research Data Manager at FAS Research Computing, and I work with faculty, staff, and researchers to better manage their research data throughout the data lifecycle. So from data generation to publication. I offer training and consultations on different topics related to data, including storage, organization, and sharing. And I also develop resources and tools for FAS that can help you track your storage usage and prepare your data for sharing and reuse. I have also been working with a few vendors to develop and refine different data transfer processes, and then also help researchers with data cleanup efforts and migrate that data through your data lifecycle from active to long-term storage. A little bit more about FAS Research Computing. So we were established in 2007. We are situated within the Division of Science at FAS, and we oversee the high performance compute cluster called Cannon. Hopefully you are all familiar with it. We also have a secure enclave for sensitive research data that's called FASI. And we offer several types of research data storage, both free and paid services, access to scientific software and applications. And then we do a lot of training and consultations related to data science and research computing. As a group, we do assist over 800 research labs. We have over 7,000 user accounts, and we manage over 76 petabytes of research storage across 3 different data centers. So we're one of the larger computing centers at an institution. We do collaborate with the Northeast Storage Exchange, or NESI, which is over at the Massachusetts Green High Performance Compute Cluster, or MGHPCC. And so we also oversee 99,000 CPU cores, 1,000 GPUs, and 1,500 compute nodes. So again, we're a pretty large compute group. So the learning objectives for today's 1-hour session, I'm hoping to have about 10 minutes at the end for questions. So if you have any questions, feel free to post them in the chat throughout the session, and we'll make sure to cover those at the end. But I'll talk about different data management policies and procedures related to offboarding that will be useful to know. I'll highlight some data organizational techniques that you should be incorporating, including directory structures and file naming conventions. I'll talk about data retention, including detailed information about some of the storage offerings we have here at FastRC and how you can use them to meet those data retention requirements. We'll review when data should be moved to long-term storage versus an archive, or even if your data can be deleted instead. We'll talk about data security, why it's important, and I'll review what data security levels are here at Harvard and why that matters for offboarding. And then lastly, I'll touch on data sharing and reuse, including why I think you should use a data repository, when your data can be transferred out of Harvard if you're leaving the university, and then how to make sure that your data is considered open access. I think it's always good just to do a refresher regarding the research data lifecycle, which is just a representation of the different stages of your research project. So the life cycle begins with planning and design of your project, and then followed by data generation and analysis, data storage and preparation for publication, and then lastly, data sharing and reuse. So your project might not exactly follow this, linear path. It might move fluidly from one stage to the next. Or there might be instances where you have to reverse course. Maybe you have to reanalyze a data set, or you acquire new data sets from an outside entity. But in general, most research projects will follow this similar path. Also, data management activities might vary depending on your discipline or your institution or your project. But in general, it follows this path. So during today's seminar, we will be focusing on the later stages of the life cycle, particularly around data cleanup, data storage, data sharing, and reuse. I will review a few topics from the first stage of your research project, particularly around data organization, as I do think these are important to consider at the end of your project as well, especially if they were not well executed throughout the project, or maybe you have to make some modifications. So why have I focused an entire seminar on the last few stages of a research project? Why is it important to review and discuss the offboarding process? A well-defined offboarding process can help with capturing institutional, lab, or project-related knowledge and documentation, which is critical information that prior lab members might not be able to convey before their departure, or if you're getting ready to close a project. So if a lab member leaves the lab or institution, you want to ensure that this transition is seamless so that your projects can maintain their momentum. And this ultimately leads to better research projects and a greater consistency between lab members. Theoretically, if you have an offboarding process in place and a lab member is aware of what is required of them prior to their departure, they can then ensure all contextual information is available to remaining lab members about their project data, and the data remains accessible and available to others and can continue to be used or even reused by other groups. In general, traditional offboarding procedures don't talk about research data. They center on other aspects of the project closeout or employee offboarding. Things like returning your laptop or forwarding your email address or speaking with HR about your pay. So things like that are generally covered in traditional offboarding procedures. So that with that in mind, we think it's important to talk about the offboarding of research data in our training seminars because it's not often shown in other locations. So here at FastRC, we have created an offboarding checklist that can help you with this process. There are several sections available depending on your role. So if you're a faculty member versus a researcher in a lab. And it also highlights different steps depending on whether you're just changing your lab group. So if you're leaving one lab and going to another lab in Harvard, or whether you're leaving the university altogether. It discusses things like your account information, your storage, maybe if you have software or hardware that you purchased, and other information. I've provided a link there in the slide. Again, I'll make sure that you get the slide deck after the seminar, so you'll be able to review this checklist in more detail after the seminar. I do recommend that you be cognizant of all existing lab department and university policies and procedures related to offboarding. There are several institutional policies that you should be familiar with that do touch on offboarding, including the research data ownership policy, which states that the university is ultimately owner of all research data that is produced and analyzed for projects at the university. And they specify that your PI or your faculty member is responsible for maintaining said data as the data steward. The research data security policy does provide guidance on how to keep your data safe and secure, especially regarding confidential and sensitive information. So this may impact where you're storing your data or how you're sharing your data, depending on the security level, which we'll go into a bit more detail later on. And then there's the retention FAQ. This is a general institutional policy that stipulates that essential research records need to be retained for at least 7 years following the end of a research project. There are a lot of caveats to this policy, so we'll touch on it in a bit more detail as well in a future slide. And then there are some funder policies that you should be aware of, including the NIH and NSF data management and sharing policies. So if you have funding from NIH and NSF, they have requirements of how you manage and share your data. And then if you are collaborating with anyone in Europe, or if you acquired data from a European entity, you will also have to be aware of the GDPR, which is the General Data Protection Regulation, which is an additional policy related to European countries. So when I'm referring to research data, I'm really referencing the scientific definition of research data, which is the recorded factual material commonly accepted in the scientific community to be of sufficient quality to validate and replicate research findings, regardless of whether or not that actually supports scholarly publications. So it's really any research data that was collected, created, or acquired throughout your research project. It could result from projects that were conducted at the university or on Harvard property. It could have been developed or collected under the direction of the university or using university resources like equipment or funding. Again, this just stipulates that Harvard has ownership over all of that data. And again, I'll talk about this in a bit more detail. All right, so as you prepare to leave your lab or the university, or you're just finishing up your project's reaching completion, it is important to review your research data and ensure that it's been organized and that you have created the necessary documentation to ensure that the data is relevant and easy to reproduce. So in this next section, I'll be discussing some data organizational techniques, as well as highlighting one of the data management tools that we've worked to create, which is called Starfish, that you can use to help with data review and cleanup. So a tangible way that you can see immediate improvements to your lab's data organization is by implementing consistent and streamlined directory structures. So for your folder structure, I do suggest that you arrange your folders and files hierarchically. So a series of nested folders, each containing files and subfolders. One recommendation is to separate your project into its own folder. And then within that project folder, you create additional subfolders based on attributes. This allows you to keep similar items stored together. This is a widely used, familiar organizational structure, so I think it's pretty ideal. And it also does a good job of representing the structure of how the information was generated. So in this example directory structure, we have a top folder for your project, and then subfolders for the data, the code, and the documentation. And then you'll notice that the data is then divided into raw and processed data, so by data type. It is good practice to keep your raw data separate from any processed data, and this is so that it doesn't get modified or lost or deleted. And then as soon as you begin to manipulate the data, you should be moving it to a separate folder as processed data. Some labs even save their raw data in a completely separate storage location, so on a separate hard drive or in a separate storage file system. This is also a good strategy. Again, it just limits the possibility of any modification or destruction of the data. The best system is really going to be the one that works for you and your project and how the data is getting generated, but this is what we recommend. Similar to the establishment of directory structures, I also recommend that you implement a file naming convention. This can significantly improve the searchability of your files. A decent file naming convention will include key pieces of contextual information about that file in the name itself. And this is going to make it easy to visually or digitally scan and discern the contents of the file. Other recommendations for file naming conventions include maintaining the same file naming convention throughout your project. Even better if you have a lab convention that is applied to all projects. Describe what the files contain and how they are related to one another. So for example, you could include things like date or project title, or maybe a unique identifier for the type of software you're using to generate the data, or maybe you're using a particular instrument, so you can include a abbreviation of the instrument name, just some sort of unique identifier in the title. And then when you're working with lots of files, or maybe you're working with multiple collaborators, you can sometimes lose track of different file versions. So you can capture the version of the file and the file name itself by including version numbers like V2 or V3. I do recommend steering clear of things like final or draft, as those can be sometimes confusing. You could also use file sharing platforms that have built-in version control, like Google Drive or Dropbox. These keep track of versions for you. Again, just determine what information is vital to your project and data sets, and then build out the file names from there. So hopefully now we've established a directory structure, we've implemented file naming conventions, but sometimes some of the information in the files can still be hard to decipher. So to combat this issue, you can record additional information about the files, including context and content about the project folder in a text file. We often refer to this as a README file. So on this slide is a nice example of a README file from Cornell. You can see there it includes the title of the data set, author information, the date that the data was collected, information about the data and files themselves. It is a good practice to store a README file within your project data set and include information about things like abbreviations or codes that were used, things that others who are unfamiliar with the project wouldn't understand just by looking at the files. If you are expecting to deposit your data sets in a data repository when your project is completed, the repository may actually ask you to provide a README file with your data set and include things like how the files were created or maybe access information, like who should have access to the data. So creating the README file at the beginning of your research project and then updating it consistently throughout your project is really going to be useful. As you're finishing up your project, you don't have to create this README file on the fly. Sufficient documentation can often determine whether your older data sets can be reused, especially if you've lost some of the context over time. Although we recommend storing the documentation as a README file in the project folder, you can also store it, say, in your lab storage, or you can even store it in a different format depending on your research workflow. So you could save it in a electronic lab notebook, or maybe create a code book or a data dictionary, things like that. No matter the format, though, there should be enough detail so that any researcher could pick up your data set and understand what is within the data set. And just, we do recommend avoiding proprietary formats. So we recommend a text file, but don't use things like a Microsoft Word document or an Excel spreadsheet, as maybe people can't access that depending on their software. So to assist with your data organization and cleanup efforts, we have worked with a vendor called Starfish to develop a user interface that will allow you to view metadata about your group storage, including storage amounts, owners, location, etc. You can log into this self-service dashboard from any web browser. You do have to be on the FastRC VPN. But all FastRC users that are associated with an established lab group will already have access. So you should be able to log in with your FastRC username and password. And then you can see trend information about storage usage over time. So if you've seen a spike or a dip in usage, you can actually see that here in the dashboard. You can also export the information as a CSV file or an Excel file. So if you want to do more sorting or filtering, you can do that way. We are still developing the tool, so we're continuing to come out with new features and new information. So please do take a look, and you'll see some new features coming in the next few months. So just a little bit more about Starfish. On the slide, you can see what it would look like, what a lab dashboard would appear as in Starfish. With some of the available metadata fields, including the folder name, the folder path, the last modified date, your data set size, and the number of files. You also can apply organizational tags to the folder names. that can help with identifying data that should be moved to long-term storage or deleted. So you can see there's a tag that says move to tape. So this is really helpful if you're going through a large folder and you have a lot of data and you want to keep track of which data is ready to move to tape or to delete, or even to keep. You can put a tag that says, please do not delete. So it's helpful with those organizational efforts. In this next section, we'll be discussing data retention, including guidelines provided by the university for how long data needs to be retained, when it can be deleted, and we'll talk about the pros and cons of long-term storage versus archival storage. So data retention is the length of time that your data needs to be kept in order to meet funder requirements and institutional policies. So I mentioned here at Harvard, you're required to retain your essential research data for a minimum of 7 years. So understanding data retention is going to help with things like budget planning and determining how long you need to potentially pay to house that data following the completion of your project. The retention period may differ depending on your funder, state, or federal guidelines. The retention could also depend on the type of data that you need to retain, the purpose for which that data was collected, any policies of the funding institutions. So if you are working with the IRB, you might have different stipulations, or if it's human subjects data. So there are a lot of factors that might affect the retention period. So before you delete any data, so let's say the 7 years has passed and you think, okay, we can go ahead and delete the data. I do recommend checking with your lab and making sure there aren't other retention policies that you should be aware of that are regarding that particular data set. The Harvard data retention policy does only apply to essential research data and records. So that's data that's integral to substantiating grant applications, published research, patents, or other funding requests, or those records considered for permanent preservation and access by the archive. So anything else that doesn't fall within those guidelines can be deleted after the project. You only need to retain essential research records for that 7-year period. So how the research data is going to be utilized and accessed is going to determine where that data should reside. So thinking back to the research data lifecycle, you'll want to lifecycle data through your storage workflow as well, from active to long-term storage. So as you begin to generate or acquire your data, you'll want to store your data in an active storage location. But then as you're finishing up your data analysis and you're no longer frequently accessing or modifying that data, it should be moved to long-term storage. Data that can be moved to long-term storage could be published data sets, data associated with finished projects, data associated with departed lab members, basically any data that's not in active use anymore. So as your project's finishing up, you'll want to evaluate your data and determine what can be moved to long-term storage, what should be moved to an archive, and what can be destroyed. Harvard has an archive or special collections unit whose mission it is to collect, maintain, and provide access to records of enduring value for historic and research purposes. So records that are eligible for permanent retention may be those that are documenting a scientific breakthrough, or they were generated by a lab or individual who had a great impact in their field, or it could be a data set that might be highly reusable for other types of research. It's good to think of archival data as separate from long-term storage. The permanent retention or archiving of data is often a significant investment for the university. It implies the ongoing migration of electronic formats. It comes with a lot of storage costs, as well as care, maintenance, and access services. So not a lot of data will end up going to the archive for that reason. As I mentioned before, the retention policies maintain minimum requirements for keeping records. So you're not required to keep your data for longer than that retention period as specified by your institution or granting agency. Often the cost of long-term storage is prohibitive for researchers, so they might not be interested in storing data after that 7-year period. And if the data does not meet the criteria for permanent retention with the archives, you can then take steps to ensure that you are safely and completely disposing of that data. Disposal of research data could include deleting it, disk wiping, destroying, or otherwise disassembling any of the materials holding the data in a way that ensures it can't be reconstructed or extracted. I do recommend creating an inventory of the records, their format, dates, and any other relevant information about the grant or project, along with the reason for the data's destruction. The benefit of documenting the disposal of research data is, multifold, including responsible management of the full life cycle of your data, but it also avoids confusion later on when people think they're missing data or data seems to have been abandoned. You can say, well, we deleted the data on X date. So it's helpful to have that record. Just a little bit more about the difference between long-term storage and archival storage. Most people use these terms interchangeably, but they are in fact two different types of storage. So long-term storage is storage of research data records just to meet the retention requirements. And then archiving is the permanent retention of research data for reuse by other researchers. The percentage of data that is deemed archival is quite small, due in part to the cost and care required to maintain them. So there's some questions there on the screen that might help you understand, when you're appraising your data, when you're looking at it. For archival value, you can answer those questions that might determine whether or not the data should go to an archive or to long-term storage. So on the slide are the various storage offerings that we support and maintain at FASRC, including our cluster storage and our lab storage. For the purposes of this training, we're really only interested in long-term storage, which is tape. So the tape storage is actually the one storage offering that's not directly managed by us, but instead by the Northeast Storage Exchange, or NESE. This is a joint venture managed, again, by the Massachusetts Green High Performance Compute Center, quite a mouthful, MGHPCC. So they manage the tape environment. Tape is designed to house data, again, just to meet compliance, publishing, or institutional retention requirements. It will not be accessible to you once you've migrated data to tape. It's not accessible to the lab or to the researcher, and therefore should not be expected to be retrieved except in extraneous circumstances. So tape storage, currently the tool you can use to move data into tape is Globus. Allocations are provided in 20 terabyte chunks. So it is a paid service. You will have to use funding in order to pay for it. And they're provided in 20 terabyte chunks. So if you have more than 20 terabytes of data that you want to move to tape, you'll be provided with multiple tapes. Tape storage comes with a number of limitations or restrictions in terms of what data is accepted. So you're limited to 10,000 files per directory, and the file sizes need to range from around 1 to 100 gigabytes in size. As I mentioned, there's no direct access to the data. Instead, the metadata will be saved in Globus, and then you can use that when if you have to retrieve data from tape. The primary reason people use the tape environment is the cost. So you can see there, the cost is only $5 per year per terabyte. There are plans to increase this price in the upcoming months, but for the moment, that is the price to purchase tape. One last thing to keep in mind with tape storage, only data that is Harvard Data Security Level 2 and below is accepted into tape. I'll talk about security levels in a future slide. So on top of reviewing your data to identify what needs to be retained, if you're getting ready to leave your lab group or university, it is imperative that other steps be taken to ensure that your data remains accessible and available to others. We do recommend doing a backup and moving personal files or departmental files from your local computer to a group storage location. So this is any data housed in personal cloud folders like Dropbox, Google Drive, OneDrive. We often find that folks think they're using a group storage in Google Drive and they're actually using personal storage. So just make sure that your files are accessible to others, either your PI or a group leader, and then transfer any folder ownership or website ownership to remaining group members. For data that's not getting moved to long-term storage or to an archive, like I mentioned, it can be deleted. Just confirm with your PI prior to deletion of the data. Make sure to store your lab notebooks and other lab records according to your lab protocol, and confirm they're still accessible to remaining group members. If you would like to transfer data out of Harvard, so you're leaving the university, but you're interested in continuing your research and would like to take data with you, you will need permission from the university to do so. I'm going to talk about this in more detail, but I did want to mention that you will need to receive permission before you can transfer data out. Make sure you remove any data that is on a virtual machine or other type of lab hardware. And then all purchased software is going to remain on the cluster. So just make sure you delegate the software license responsibility to your lab or department. So as I mentioned in the previous slide, you might have the desire to transfer data to your new institution when you're leaving Harvard. You will have to make sure that you get written approval from the Vice Provost for Research. And you're also going to need written permission from your new institution that will guarantee Harvard access to that data set if needed. And then also Harvard will maintain a copy of that data set here. And again, this is because of the Harvard data ownership policy. So the university owns all the research data, and so they'll maintain a copy. The best way that you can transfer data from FastRC storage to either your new institution or somewhere else is with the same tool for tape, which is Globus. So for this next section, we'll talk about the Harvard data security levels and how they play a role in terms of offboarding. I have some general recommendations for how to protect and back up your data. And we'll touch on the FAS Secure Enclave Environment, or FASE, and how that also plays into offboarding. So understanding data privacy and security requirements is really necessary, especially if you have sensitive and personally identifiable information. Most institutions, including Harvard, have different security levels for research data. So Harvard has a 5-level data security system that indicates what tools and platforms you can use depending on the different level. So it starts from level 1, which is publicly available and unrestricted data, and goes all the way up to level 5, which is very sensitive data that could put someone at severe risk of harm. At FAS, we support level 1 and 2 for our Canon environment, and then level 3 in our FASE environment. If you have data that's considered level 4 or 5, you'll have to talk with other groups on campus to see if they can accommodate you, including the University Research Computing Group. One straightforward data security strategy that I recommend is the 2-2-1 rule. So this rule stipulates that you should be retaining an extra copy of your data on a different type of storage, and that other type should be offsite. So for example, if you're generating data with an instrument and it goes to your lab computer, that's your raw data, you should have a copy of that made either using a tool like CrashPlan, which will back up those files to a cloud resource, or to an external hard drive, or some other backup option that is separate from the lab computer. So this just makes sure that your data is spread across multiple types of storage and diffuses the risk that data could be lost, or you wouldn't have another copy. This also prevents total data loss due to localized events like fire or flood or theft. The ideal backup system is going to be one that fits into your research workflow and accounts for the speed and scale of your data production. Once a backup system is implemented, I do highly recommend you take the time to learn how it works and how to restore the data. It's much less stressful to figure this out when you're setting it up versus when you're panicking because you think data has been deleted or you have a crashed hard drive. It's also recommended to periodically confirm that those backups are working and to, again, avoid any unpleasant surprises when you're trying to recover data in a crisis. So as I mentioned, FASI, that's our secure storage environment for data analysis or sensitive data. We often use this for data that's generated using a data use agreement or a DUA, or in conjunction with the IRB. It does adhere to standards required to house data up to Harvard Security Level 3. We ask that all FASI projects be reviewed and decommissioned prior to your departure if you're a faculty member. You can submit a request to FASRC specifying what needs to be deleted or removed, and then indicate whether that data has an associated data use agreement. Most data use agreements specify when the data needs to be deleted, so it's great to know what that time frame looks like. Moving on to data sharing, we are going to focus on why it's worthwhile to share your data and what specific tools you can use. A key aspect of data management involves not only making your research product, like your article, available, but also any associated research data, code, and other materials that you produced as part of your research project. I'll also touch on what it means to have open access data. So in order to publish your data, we're going to need some sort of infrastructure to help support this, as well as the discovery and long-term accessibility of your data. And so this is the role of repositories. So it used to be acceptable to share your data on personal websites or even put it in a shared location like Google Drive and just link out to it in your article. Now it's not really acceptable to do that. Oftentimes this doesn't meet the requirements for grant funders or scientific journals. They're going to require that you actually put the data in a data repository, as they provide the technical infrastructure for access and curation, and they also provide a framework for you to describe your data using metadata standards. They're also great because they do supply a persistent identifier or a DOI, basically a citation for your data. So you actually receive credit for your work. And there are a lot of different types of repositories you can use, so you can find the right platform that'll work for you and your project. So there are generally three types of data repositories. You have institutional repositories, disciplinary, and generalist. Institutional repositories are for researchers at a particular institution who may be required to share their work there. We use Harvard Dataverse here, even though it's technically a generalist repository, but it was created at Harvard, so we recommend that one. But you can also have repositories that are associated with schools like UMass Chan. Princeton has their own repository. A lot of institutions might have their own version of a repository that they require you to use if you're at that institution. And then you'll have disciplinary repositories like dbGaP or GEO for genomic data. These are targeted places for certain types of data. And then generalist repositories are really for any type of data, and they also accept other types of research outputs. So typically you'll go from left to right. So you'll start by identifying whether or not you have an institutional repository. If you don't, look into whether you have a funder stipulated repository. And if they don't require you to put it in a particular repository, then you can move on and use a generalist repository. For data generated from research with no data repository specified, researchers are encouraged to select the data repository appropriate for their data type that still meets, the desired characteristics as outlined by like NIH and NSF. So what do generalist repositories offer? And what should you be looking for when you're selecting a repository? So here are some of the advantageous characteristics of generalist repositories, including unique and persistent identifiers. Again, so giving you credit for your data sets, the long-term sustainability of your data sets. They also meet granting and funder requirements for data retention. They can help you with adding metadata, and you can even pay for additional data curation. So if you don't have the time or energy, or you have extra funding and you want to have someone help you with the data curation, they do offer that as well. They offer free access to open data sets. So not only can you deposit data in a repository, but you can actually look for data to utilize in a repository. They offer data security and access controls. So they allow you to either restrict your data set or open it up to the general scientific community. They allow for deposit of most data formats, and they support this concept of fair data. And you might say, what is fair data? Well, fair data principles, they were published in 2016. They are a guiding principle that encourage reusability of digital research. So ideally, your research should be findable, accessible, interoperable, and reusable. There. And most data repositories meet these criteria. So you can use these principles as a guide and ask yourself, is your data findable or discoverable? Is your data easily accessible to others? Can the data be accessible from different devices? So is it in a format that would be available to everyone? Is the data reusable? Does it contain enough context and information to be reused by other researchers? So that's the general idea. So I mentioned Harvard Dataverse. This is the generalist repository that we recommend. It is a free web-based data repository open to all researchers from any discipline, both at Harvard, but also outside of Harvard. You can share, download, archive, cite, and explore research data through the platform. You can open your data up to the general public, or you can restrict access and define what those terms of use are. And your metadata is open and findable via search engines, even when the data is restricted. So you will still have it discoverable via tools like Google, but they just can't access the data itself. So you still get credit for the work, but you can restrict who has access to the data. You can deposit up to 2.5 terabytes for free. There is additional storage available for a fee through Harvard Library in collaboration with IQSS. So if you have more than 2.5 terabytes, I recommend that you reach out to the representative at Harvard Library and just speak with them about it, and you might be able to get additional storage. It's discipline agnostic and holds up to level 3 in terms of data security. So like I said, data curation services are available from the library. They can help you offset some of that labor and administrative work associated with creating and maintaining those data collections. I also wanted to mention Dash because I don't feel like a lot of people know about Dash. So Dash is Harvard's central open access repository for manuscripts and articles. It's also managed by Harvard Library, the Office of Scholarly Communication. The articles are free to download. They're open to everyone, and they're free from most copyright and licensing restrictions. So I do recommend that you store your article in Dash and your data in Dataverse. The nice thing about Dash is that it also supports browsing and search capabilities. And you can actually find articles that are in Dash through Hollis, which is the library catalog at Harvard. So open access is this international movement that is seeking to grant free and open online access to academic information, including publications and data. So publication is defined as open access when there are no financial, legal, or technical barriers to accessing it. So anyone can read, download, copy, or use the information. There are two major ways that you can have open access publications. You can either publish in an open access journal, or like I said, you can deposit your publication in an open access repository like Dash. Lastly, we'll cover some additional considerations around deactivating your FastRC account, and then just some further offboarding procedures provided by FAS. So FAS RC accounts should be disabled when your appointment ends, along with your Harvard email address. Disabling your account will automatically remove you from associated groups. If you do need to maintain a FAS RC account following the end of your appointment, you will need approval from your PI or authorized lab member, who can email us directly prior to your departure and ask for an extension. Your account will then be converted to an external account, and you'll be given an additional 90 days of access. Once your account's disabled, you'll no longer have access to our storage or cluster. One thing to note, though, if you are moving from one group or one lab to a different group, you still retain your home directory. So this is associated with your FastRC account. It's not associated with a particular group. So we do get that question enough, where they say, I'm moving from one lab to another. Do I get to keep my home directory? And the answer is yes. So in addition to the considerations that you should be aware of regarding offboarding of research data, FAS also has additional requirements that can help with streamlining this transition. These are the more traditional offboarding procedures, talking to HR, forwarding your email, returning Harvard property, etc. So I won't be going into detail about these, but you can review them again after the seminar. I just wanted to note them as they are good to keep in mind. And I'm going to stop recording.